Okay, hello, good morning everyone to this talk. First of all, thank you very much for inviting me to give this presentation on 5G and why real time is very important to 5G and why it is also very important for you. My name is Jorge Garrido from Huawei, and let's start. And let me disappear from the screen so you can better see my slides. Okay, so this is the outline of the talk for today. It's only 4 points. We will first briefly describe what are real-time systems, then why they are important for us and for 5G. In third place, we will see which are the problems to build real-time systems. And in fourth place, and to finish, we will see in the end how we can still build these systems, these complex systems nowadays. So first of all, what are real-time systems? Okay, we will give a very short and simple description in which we say that in general it is any system that is required not only to provide the correct output but also to do it at the proper time. I have highlighted 3 words here. First is required, so it gives the idea that we have some requirement, some formal thing that we need to meet. Second is that, of course, we still need to provide the correct output. The system still needs to be reliable from the logical perspective. And finally, and what it makes real-time system what they are is that the time in which the response is given is especially important. So second point is why are these systems really important? Well, probably you have been in this situation many times, or at least a number of times, in which you are driving your car, you put your GPS to arrive to some destination. So you are, in this case, riding on central Stockholm. You are about to reach your destination. You just need to make a right turn here to arrive your destination. So you are driving and progressing on the street, waiting for your next instruction from the UPS. But sometimes the GPS starts lagging behind. So at the end, when you have already passed the crossroads, then the GPS reacts and tells you, oh, you have to turn right on Kungsgatan, which is unfortunately the street that you have just passed. So of course, in those cases, you get really angry with your GPS. So let's, by the previous definition, examine briefly what happened here. Well, we have this system, in this case the GPS, which delivered the correct action. You should have turned right on that street. Problem here is that action was delivered at an improper time. In this case, this was delivered too late. Here we have another example of a real-time system in which delivering response in time is really important. Here the problem is not only that we may not trust Homer to be the best one to handle with a problematic situation on a nuclear power plant, but also if he is sleeping while most indicators are getting in the red zone, we are pretty sure that he will not be able to give a proper response in time. Quite similar in this situation in avionics. This is another typical area of real-time systems. And in these 2 cases, we have seen, or 3 cases, we have seen situations in which delivering a response too late is a problem. But we have to bear in mind that also sometimes delivering the output too early might also be a problem. For example, closing a door too early, that can be also sometimes a problem, as we can see in this picture. So in real-time systems, we need to provide not only the correct response of the system, but it also needs to be delivered at the proper time. We have seen some use cases, but sometimes there are some more others related to 5G and in which real-time systems have something to say. We have these 10 use cases from our colleagues of Huawei X Labs, and we can see cloud virtual and augmented reality. We'll see some samples later. Automotive, we've seen energy, wireless e-health, more examples also ahead, and many others that probably you have already heard that 5G can make a change on these areas. One example here we have is a Huawei first 5G enabled remote surgery of an animal, in which we can see this doctor doing this surgery to an animal from 50 kilometers away. You can imagine that in this case, having a good latency, it's really important for the good or the proper output of the surgery. You need to have and also good bandwidth. Here we have the doctor seeing in a high definition 3D image of what's happening in the surgery in the hospital, while he is acting on these remotes that need to be really small latency, so he can actually feel what he is doing on the body of the animal instantly, like if he was actually doing it with his own hands there. And of course, the reactions of the doctor need to be transmitted in the same way, really fast to the hospital. So the actions are done almost immediately. Another 5G example in which Huawei has also been working in the past, and it's now something that is commercial now. It's in open pit mining. This is a very risky industry or process in which we have many different actions that are actually really risky, that like drilling, of course explosions, also loading tons of materials on trucks, transporting them, and also the processes that are done on this material. So what Huawei has done is to enable a solution in which both mining trucks and excavators can be remotely operated or autonomously remotely operated by installing GPS antennas on trucks and also cameras on vehicles, and some unmanned driving control on the vehicle, which is connected via a 5G base station to a remote place in which the control algorithms are executed and are transmitted back to the mining trucks. So from the requirements, which I mentioned before, we can see that this scenario could not be possible with previous 4G technology, because we need at least 2-channel video data for uplinks composed by 8 megabits per second, and also 1 channel for downlink bandwidth of 10 kilobytes. That of course could be done with 4G, but clearly not the uplink, as you can see. And more important is from the point of view of real time, from the timing perspective. For this to be feasible, this scenario to be feasible, the latency of the network was required to be below 30 milliseconds. Because here you can see for the general requirement for the latency is that if we want these tracks to ride at 30 kilometers per hour and to be able to break it in just 1 meter, we require the overall latency of the system to be 120 milliseconds, of which 50 are budgeted for mechanical conduction, for applying the brakes themselves, 30 milliseconds for video processing at the remote place, 10 milliseconds to detect that actually we need to brake, and yes, there are 30 milliseconds left for communication. So clearly we can see that this is something that could only be done with 5G. So for the examples we have already seen and many others, we have to bear in mind that these sectors in which we would like to apply 5G and real-time systems are most of them regulated, which means that there are specific regulations for software products, including real-time requirements and guarantees that need to be provided for the system to be actually built and deployed. We have the examples of avionics. We have already seen a picture of that. Cars, trains, processing, machinery. We have just seen another example. Nuclear plants, and there are many others. And with all these rules and guidelines, the thing is that it's not only that you have to follow them, but it's that you need to prove someone else that you have followed them, that you have the guarantees for those real-time requirements, and that needs to be approved by someone else. Okay, so now that we've seen that real-time systems are important for us and for the many systems that we use every day, let's see why they are nowadays difficult to be built. Well, the main problem is that computers nowadays are too complex and are non-time deterministic. We will see why. But also, telecommunication systems are too complex and too non-deterministic too now. For those of you that have studied, for example, how protocols on the internet work, you have heard most of the times best effort, and best effort is not real-time guarantee, is best effort. Okay, so bear that in mind, please. Okay, from the computer perspective, which is the traditional area of real-time systems study from the software perspective. So here we have the scenario when first computers arrive. We have this von Neumann architecture in the around 40s of last century, in which you have a very simple computer with some memory, a CPU, which was something quite simple from nowadays perspective, in which some information comes in and comes out, and there is not much more that we need to know from the inside. So you have this program, this small program, or this few lines of a program in assembler code. Of course, it's writing on a papyrus because it's something really, really old. And when you want to have an analysis of the time it will take for the CPU to process these 4 lines and provide the output, it's quite simple, because for the CPU you clearly know and you deterministically know how much it takes to execute each of the instructions. So you just add the cycles that are required for each one, and you have the final number of cycles that you will need for executing this, and then you just translate it to time, and there you go. So, but things got more complicated with time. Almost some decades after that, first high-level programming language appear, like for example Fortran. So you could build more complex software. Here we have some few other instructions, now more complex than those we saw on the assembly code. They are now also on a tape because it's a little bit more modern. And the things that what we can express with this higher level programming language, now they are more complex, and we have less information, and we could have less assumptions on, for example, what are the values of variables. So now to calculate how much time it will take for this to execute, we have to make some assumptions on, for example, what are the values of the variables. So we now have not only one answer to how long it will take to execute this, but at least, for example, 3 different possibilities. After that, probably next big change was the more complex CPUs, for example, pipelines, in which we can now more or less have more idea what's going on inside the CPU. It's clearly divided on different stages, the execution of each instruction, and how fast one instruction evolves also affects how will previous ones will, or next ones will take to execute. So we are adding more uncertainty on how long it will take to execute it. Not only what are the values of the data, but also the dependency among the instructions in which this code translates to the microarchitecture, etc. So now for these few lines, we have tens or dozens of potential execution times for this code. Next big change was the appear of complex operating systems in which you can make these calls to the operating system, which are parts of the code that you have not written, so you can barely know how they are implemented, and it's difficult for you to have an idea of how long they will execute. So when you are doing the timing analysis, you have to consider all the previous if situations, all the potential conditional situations, and also how long it will take the operating system to serve your calls. So now you have maybe hundreds of potential execution times for your code, for your simple code. Next big change, maybe the appearance of cache memories in 1975 mainly. So you have all the uncertainty from previous steps, and then your execution time also depends on if your data is in cache. It's fully allocated in cache. It's nothing allocated in cache, just a few instructions. Each is your data, but not your instructions. So the number of potential execution times keeps growing and growing. And from them, there have been also many other changes on computers that make them more complex, provide, of course, much better average performance. But when you think about the worst case execution time, how long it might take something to execute, it makes more and more difficult to calculate. Here you have some more examples from the hardware perspective, operating systems, again, multi-core, multi-processors, and including some new paradigms like virtualization or complex virtualization with, for example, containers, etc. And these factors keep growing over time. So okay, we have tried enough for now, and now let's see what we can still do to build real-time systems. Okay, so here we have what I call the real-time system magic formula, things that you need for building a good real-time system. First of all, you still need a reliable code. You need a code that will provide the correct output every time. Then you need to be able to predict which will be the execution time of your code. And finally, you need to properly schedule things on your system to finally have what we call a feasible real-time system. We will see step by step all these things. So we build this by using particular in what we call the predictable execution time. We have seen that hardware has gone too complex over time. So in general terms, we use hardware that is specifically developed for a real-time system. We have several vendors building different kind of hardware specific for, like Texas Instrument, the ARM Cortex R processor are also addressed for real-time system, Leon processor from the space sector. From the point of view of the operating system, there are also specific real-time operating systems which are quite basic if we compare them for general purpose operating system, or just small kernels that barely only provide task scheduling, process management, and not much more. Here we have some examples. And next, I will mainly focus on building predictable and reliable applications, what we can do as coders to build real-time systems. Okay, so I will focus on timing predictability, but some of the things that I will mention also relate to reliability of your code. So, for example, when we talk about types or variables, one thing that it's typical in real-time system is to use a strong typing languages in which you are not allowed to mix different types. For example, like you can do in C, that you can barely add two variables containing any information without that being an error. This is not only to consider reliability, but also to be able to guarantee the execution time that it will take to do this add operation. And this is strongly related with using static types, okay, in which all types are declared and at compilation time, and that can be checked, as I mentioned, at compilation time. So the types are known a priori and can be studied and analyzed before executing your code, the time it will take to do any type of operation on your variables. Also, something important are safe pointers, what we call safe pointers, and by safe pointers we refer to pointers that can only point to objects that have already been declared, that you can make a pointer to point at them. So you cannot point to everything, just things that have been declared. Some languages allow you to declare that pointers cannot be null, and that can be checked at compile time, so you don't have these typical errors of null pointer exceptions. And also you can avoid having runtime errors like array auto-bind exception if you are, for example, using Java, by not doing incremental operations over pointers, but using indexes from maybe from static types that you know that how long is your array, so you cannot so you can check at compile time that you can go over that index. From the memory management perspective, what we can normally real-time systems are restricted to not using dynamic memory allocation and thus not creating objects at runtime. Let me showcase why. Okay, let's see this small example and consider that this is from a nuclear power plant in which you have to handle an emergency situation and you need an amount of memory to process your algorithm. So you request the operating system this kind of memory, this amount of memory, and what do you do if now the operating system cannot provide you this amount of memory? Well, typically what you do is to abort your execution, but then something bad, really bad, will happen on your nuclear power plant. So this is something that you cannot have on these kind of real-time systems. Or even worse, you could say, okay, let's wait until I have enough memory, but let me believe me that this is still, or this is even worse to do this. Okay. So no dynamic memory. As a consequence, other more modern things for memory management like garbage collection, it's something that we do not allow also on real-time system, because normally we don't know when it is going to be triggered and how long it will take each time the garbage collector executes. And also as a consequence, normally it is not allowed to create or terminate threads or tasks. So what you typically do is create them all at the start time, and then you release them when you need them. Okay. So There are many other things related to code that are related with real-time systems that I cannot cover everything. I will give you some information on how you or where you can find more information, but for the moment, let me stop being negative on code, restricting things, and be more positive and explain you some things that modern real-time system languages are providing for real-time systems that are, for example, contracts. Contracts are formal specifications of types and program behavior that can be checked, normally both at compilation and runtime. Normally you can also stop doing these checks at runtime to save time, but clearly the power is at compilation time that you can do a lot of static checks. And the idea of this formal specification is that you can formally prove your program to not have undesirable properties. For example, can be proven to not write exceptions or not some kind of exception. We will see an example in a moment. And increase the reliability of your code, both by the automatic checking itself, but also by the programmer reasoning about the code twice, one when writing the contract and then again when writing actually the code. And typically we see that a subprogram contract, for example, includes a precondition and a postcondition. So we will see an example of this function that is the sum of two numbers and returns another number. Okay, so we have this precondition that each of the input parameters, they need to be equal or smaller than half of what you can represent with a number. So the result, the postcondition, is that the result will be the addition of a plus b. If any of these two numbers will be bigger than half of what you can represent with the number, you cannot prove, for example, that you won't have an overflow of what you can represent with number. Okay, so this is a simple example, but I think it can show the power of what you can do with this. Okay. Regarding programming languages, you can, in theory, write your real-time system in almost every language. The problem normally is what you have behind, your runtime, etc. But technically, you could try to do it on every single language. But of course, there are more specific languages that will help you do things better from the real-time perspective. One of them, probably the most used, is Ada. Ada is an ISO standard language, and it's mainly used on space, aeronautics, railway, power plant, etc. Okay. For the previous example I showed you, was a contract writing for an Ada program. Your main alternative to use Ada is using C, but what it's called MISRA-C, which is a set of software development guidelines. There is MISRA for C and C++. This is an industry de facto standard, so there are documents from industry that you can follow and you can find for building MISRA-C programs. And this is mainly used in the automotive sector and normally in some other sectors, not those mentioned before, in which the level of warranty you have to provide sometimes is less restrictive. Okay, so we want to have to know the execution time I mentioned in our magic formula. So now that I have talked a little bit on how you can build predictable software pieces, okay, so let's try predict the execution time of those pieces. Okay, so typically the traditional way was to do a static analysis in which you have your program. You do some kind of flow analysis. This is to detect which possible conditional flows of execution can have your code. So you have some call for facts, we said. Normally you help also this process by adding annotations to your code, normally, for example, to restrict potential values of parameters, these kind of things that can help doing this analysis. And you also, in parallel, try to know how long it would take to execute the small pieces that conform your flow analysis, everything that is non-conditional from the logical perspective of your code. And you do this in the static analysis by using a timing model of your hardware. This means to having a model of your processor that can tell you for each instruction from every line from your code that generates each instruction, how long it will take to execute this. So you have what we call atomic worst case execution time for each small piece of your code. You mix it with the information that you have from your call flow of your general programs, and there you have your execution time prediction. Normally, we will see we are mainly interested on knowing the worst case execution time. How long, as much can your program take to execute? Nowadays, however, as systems are getting complex, we use what we call dynamic hybrid analysis, in which normally everything on the left side you do it as in the static analysis, but to have this information on the execution time of small pieces, instead of use a hardware timing model, what you do is to add some instrumentation to your code. You compile it, you generate an instrumented binary of your executable, and you actually execute it on the real hardware. You do some executions, so you get finally these values of how long it will take to execute those small pieces on your real hardware platform. And again, you mix everything, and then you have your worst case execution time. So static analysis is more reliable, but has two problems. One is you need to have a very accurate model of your processor, and can be quite pessimistic. And dynamic hybrid analysis is good in the sense that helps you because you have your real hardware on the test. But the problem is when you are testing, you can never guarantee that you have seen your worst case execution time because of the complexity of the platform. Okay. Final step is in our magic formula is to do the scheduling, which is to decide what to execute on every instant. And this what to execute, normally we call them tasks, which are the different threads of execution of your program or the piece of code that you are thinking of. And these are defined by the worst case execution time, the deadline, which is the time by which the response has to be provided, the activation pattern. Normally we like things to be periodic, things that you do every some time, but in reality most things happen periodically or sporadically, but we try them to be modeled as periodic tasks using what we call minimum arrival time. And sometimes you also want to give some priority to tasks. Okay, so when we think about the scheduling, when we represent it, we use normally a timeline that time moves to the right, and each task is as long in this timeline as the worst case execution time, how long it will take to execute on time. And we use arrows to represent normally the activation pattern. When on each of these arrows the task will be released again, and normally the deadline is equal to the period. So at this arrow we need to be finished with this activation because we will have a new activation here. Okay, so we'll see a fast example with 3 tasks. This task 2 has a shorter period and shorter execution time, and task 3 has a longer execution time and longer period and deadline. Okay, and this is the CPU. We have a single CPU example in which we have to execute, on which we have to schedule what we will execute at every single time. Okay, so we will see first one typical case of a scheduling algorithm, which is EDF, earliest deadline first, in which basically we execute the most urgent thing at any time. So for example, here, the first thing we will execute is T2 because it's the one with the deadline which is closure. Then we execute T2 because we have its deadline, and then we execute T3. But at this point, we have the new activation of T2, so we preempt T3 to let T2 execute because its deadline is closer than T3. Then we execute T3 again, and then T1 and T2. In this last execution of each task, since they have the same last deadline, we'll just let them continue without preemption. The other main general case is when we want to do overscheduling based on some kind of priority. So imagine that the priority goes from top to bottom. So T1 is the highest priority one, and T3 the lowest priority one. So in this case, we start executing T1, then T2, and then T3 until we can execute it again T2. We let T3 continue again until T1 is ready to execute again. Then T3 has the most chance to execute here again until T2 is ready, and finally we finish with T3. Okay, so these are some simple examples of scheduling, but things can get really much more complicated when we have more complex system with different operating modes, transient mode or transient states between modes, etc. When you have worst case execution overruns, even if we take much care of calculating worst case execution time, sometimes we were not safe enough with our calculations, and something took longer than expected to execute, maybe like this talk. So we need to do things to manage this situation. We've seen also an example of 3 tasks that had no dependency among them, they were unrelated. But normally when we want to accomplish a complex situation, a complex program, our flows of execution are some kind of related and need to cooperate to get the final result. In our system, we also tend to have shared data on resources that we need to take care when handling them, to not have concurrency problems like deadlock, light blocks, etc. And of course, multiprocessor system makes things much more difficult because we need to share some certain parts of hardware that are not replicated. And when we are doing the scheduling, you have to consider in which processor are you going to execute each thing, if you allow things to migrate among processors or not, etc. And many others and many combinations of these problems. Okay, so scheduling algorithms nowadays are much more complicated than what we have seen, but they were just simple examples for this presentation. And this is my last slides, and I want to use it to put in some context what we have seen with nowadays communication problems, okay, and 5G. And in 5G and in the situation that Huawei is providing its services is to solving what is a twofold problem when you have a 5G base station. One is that you have to schedule your communication resources. This is, you have to schedule how you are going to provide services to your users. And this scheduling, scheduling your users is something that you have to execute on your base station. You have to execute this algorithm. And this algorithm, both the users have real-time system requirements, as we have seen, but you also have real-time systems requirement to do this scheduling. So that's why we say we have a twofold problem. Let me put an example. Imagine you have a football stadium in which you have thousands of users which have different quality of services that you have to provide them. For example, imagine you may have tens or dozens of cameras transmitting on 5K quality video, And you have also thousands and thousands of users that want to make use of 5G enabled technology, for example, augmented reality, in which they need to have really low latency on the data they receive to be able to put this data over what they can see with their bare eyes on the field. And to do this scheduling, you have not only many users, but also to consider many parameters. For example, the signal quality of each of these users, how much data wants to transmit each of these users, and how much is available at any single time. You not only give your users some time to transmit, but also you can give them different bandwidth. This is something also new from 5G in some cases. And of course, you have to bear also in mind all the inherent problems of radio frequency communication, for example, losing messages. And why this is a big challenge nowadays, we'll give you some historical point of view here now. In the past, I was involved in the space sector, and I worked on for a company doing some similar things for satellite communications. And in satellite communications, the period of transmission that you allocate to your users is of 67 milliseconds. Okay, this was something that we had to solve like 10 years ago, how to do that. And nowadays, periods in which we have to do the scheduling for users nowadays are 1 millisecond of lower in 5G technology. So you can see that the problem is not only more complex, but also the time requirements for our base station to do this are much more short in regarding time and our deadlines. Okay, I said this was last slide. It was not really true. I wanted to provide you this. These are 2 books that you could use if you want to learn much more about real-time systems and how to build them. And in particular, I selected these 2 because they both give a very big picture idea and cover most of things related with building real-time systems, and they provide many examples of code. The left one mainly just C, and the one on the right, real-time systems and programming languages, includes Ada, real-time Java, and C mainly. Both of them you can find them on Amazon. And also you can find on Google many material from this book provided by the authors, like slides, examples, etc. So I recommend you at least Googling the titles to check what you can find on these books. Okay, this is all from my side. Thank you very much for following this talk. And now I will be really happy to answer any questions that you may ask. I really appreciate that. Okay, I think general process is that if you have any questions, you can type them on the chat. Okay, we have first question from Herman. Do you think that real-time systems will become easier or harder in the future with faster computers and more complicated programs? Well, from what I have already presented, no. I think the real-time system will become much more complex because faster computers are building in general more complex hardware architectures. Let's see what quantum computing can provide in that sense. But I don't think that it will be more simple from the timing perspective. And of course, more complicated programs. Yes, the more complicated, the more difficult to be able to predict things. Another thing is how much you can build some kind of composability of the system. If the system gets more, or your programs get more complicated, but you can divide them on clear different sections with clear interfaces, and you can provide warranties on each of the sections, and then put everything together. That makes things much more simple, but still, the more complicated, the more difficult. More questions, please. Okay, don't be shy. You can make any other questions. Okay, if not, you don't have any other questions, I think we can finish here this presentation. Thank you very much again for attending and for giving me this possibility to let you know what we are doing here on Huawei. Oh, we have another question for Herman. Thank you very much. Could open source hardware help to make the timing easier to reason about? Yes, clearly. One of the problems when you try, for example, to apply static analysis is that, as I mentioned, you need to have a very accurate timing model of your processor and of your system in general, but particularly from your processor. And that's very complex nowadays because, as I mentioned, it's not only that processors get much more complicated, but it's more difficult to get the information on how they are built and which is the behavior of these processors in at the small level that we need them to be able to predict what will be the execution time of each instruction. So clearly, with open source hardware, you can actually study that open source of the hardware and be able to do predictions. For example, I mentioned Leon processors that are mainly used in space. These are processors that are not only more simple, but are defined in VHDL. So it's something that you can synthesize on your FPGA, for example, and there you can, since this is defined of VHDL and you have all the source of definition of your hardware, then you can make your analysis from this static point of view, because the model, it's the real hardware, let's say, because you build your real hardware from the model that you already have. Okay. I don't know if there might be any other question. I will maybe give a short example of a problem from real time, real situation of real time problem. Maybe to give you time to give any other question. This is from a typical example. It's a Mars Pathfinder, which was the first rover to be landed on Mars, and it has a number of instruments on board. And after a few days from landing on Mars, its computer started rebooting every now and then, and this was due to a real-time problem. We said that when you have a worst-case execution time overrun, when something takes longer than expected to execute, you need to do something to protect yourself from that. Sometimes this is to just reboot the system to check if that solves this transit problem. And this was what's happening on Mars. They had this task doing some meteorological measurements that log mutex on the system, then some intermediate priority tasks, and then a very important task that had to be finished by a certain deadline that was getting activated, and then required the log that was acquired by the lower priority task of the meteorological instrument. And the thing is that due to this intermediate priority task, the meteorological task was not able to release the log, and then the high priority task was exceeding its deadline, and the computer was being rebooted by an automatic protective system. So this is a clear case of a real-time system problem on a very, very complex system in a very expensive system. Thanks, nobody was in risk here. It was only money and many times or a long time of research. But these kind of things can also happen in systems in which lives of people are at risk. So this is why you need to be able to provide warranties from the real-time perspective on those systems. Well, okay, I don't see any further questions, so let me just finish and close this transmission. Thank you very much for attending this presentation again and for inviting me.